Good day, students. Welcome to our another online session for the course Computer Organization. And in the previous session, we have discussed about the single cycle processor and its implementation. And we have seen different cases. For example, we have seen that how we'll implement the R format instructions. Then afterwards, how we'll implement I format instructions in branches and jumps and loads and stores. And we've discussed that in detail. And in the previous session, we have focused on implementing the jump instructions as well as the branch not equal instruction. We have seen the case for that, and we have ended our discussion on performance issues regarding the single cycle processor. And we have said that the performance is basically dependent upon the slowest instruction, and because all the instructions will have to be executed in one clock cycle, and the clock cycle time is determined by the slowest instruction or the critical path of the system, and that was the load word instruction that basically determines the clock cycle period so that all the instructions can be executed. And we have also seen the scenarios that some of the instructions can be executed earlier. For example, the jump instruction is the shortest instruction that only utilizes the instruction memory for the machine code and some additional digital hardware. So the instruction which is most affected by this is the jump instruction. For example, we can complete the jump instruction in 1 nanosecond, and the load word can be completed in 10 nanoseconds. So we have to set the clock cycle time equals to 10 nanosecond. So what happens to the additional 9 nanoseconds for the jump instruction? So that are the wasted time. So we cannot do anything in sequential processing or in single cycle processor. So another thing that if we are utilizing the data path for the single instruction, we cannot utilize the functional units that are idle for the other instructions unless and until the instruction is completed or performed its functionality. So we cannot process other instruction in the same time as we are processing the current instruction. So what we have to do is we have to go to those scenarios so that we can overlap the execution of our instructions, and we cannot make or leave any of the functional unit idle or doing nothing. So we will make them busy in such a way that multiple instructions can be performed simultaneously so that we can perform multiple instructions at the same time period, and our throughput of the system can be increased in that particular fashion. So we've got the idea of pipelining. The pipelining is basically the idea is a methodology of overlapping the execution of the instructions, or we can say that concurrency can be achieved by pipelining. In today's session, we will be focusing upon the pipelining. What would be the benefit of pipelining? We would analyze a piece of code for the single cycle processor as well as for the pipeline processor, and we will see how the performance is improved in a particular way. Well, to understand the pipelining concept can easily be understood by the laundry mechanism. For example, you have to wash your clothes, you have to dry your clothes, you have to press your clothes, and you have to hang your clothes. So at a single time for the single task, for example, we've got different tasks A, B, and C, D. We can resemble those tasks by the instructions. So what we can do is that first of all, for each task, for each load, basically we have to run in a sequential order if we are using the single cycle processor. So first of all, we have to wash our clothes, then we have to dry our clothes, then we have to press our clothes, then we have to hang our clothes. So we are basically not overlapping the execution in a single cycle processor. If you can see that the first timing information on the diagram that suggests that at which clock cycle we are performing which operation. So if you see that at 6 p.m. we have started our laundry, and from 6 till 6:30 we have washed our clothes, and then at 6:30 till 7 we have dried that load. But when we are drying that load, the washing machine is free basically, isn't it? But in a sequential processing, we cannot run the other load at the same time. That is the restriction in a single cycle processor. So if we are pressing the clothes, the dryer is also free and washing machine is also free, but we cannot process other applications or other loads at the same time. So for the first load, all the four steps are completed. When those four steps are completed, then at that time instant we are loading the other job, which you can see that. And when that time instant is completed, then we are loading the other job. So we cannot do anything here this time in this time if we are making the arrangements for the clothes, or we are arranging the clothes while the presser was free, the dryer was free, the machine was free. So the pipelining suggests us that we can, if any of the functional module is free, then we can process the other batch or the other job at the same time. So if you can see that for the task A, we have we have washed the clothes at 6 p.m. and when we are drying the clothes by using the dryer, we have at the same time we have loaded the other job, other task. So we are not leaving any of our functional modules idle basically. So we are basically overlapping the execution. So for the first situation, the scenario, you can see that we have started at 6 p.m. and we've got our jobs done at 2 a.m. next day. But for here, if we are overlapping the execution, we have started the job at 6 p.m. but we're free at 10 a.m. So this is the benefit which we have got by using the pipeline system. So for loads, what would be the speed up of this system? Basically, if you can see that speed up is equal to 8 divided by 3.5. Now where does this 3.5 come? Anybody, if you can analyze that, uh, speed up is equal to execution time old divided by execution time new. That is, we've got the whole task done in 8 hours, starting at 6 p.m. till 2 a.m. For the non-pipeline system. And for the pipeline system, the same task can be performed in 3.5 hours. So execution time old is 8 hours divided by the execution time new, that is 3.5 hours, that is equal to 2.3. So definitely a performance is more than double in that particular scenario. One important thing is that speed up is also dependent upon the number of stages, and number of stages are dependent. We will see that while we are converting the single cycle processor into the pipeline processor, that how we're going to identify the number of stages. Basically, that is dependent upon the number of functional units minus one, or the number of registers basically which we are using in order to implement the pipeline system. We will discuss that later on while discussing in that thing in detail. So for the MIPS pipeline, we are using the 5-stage pipeline. The first stage is known to be the instruction fetch stage. That consists of that hardware that is used to fetch the instructions from the memory, and definitely for the MIPS processor, we are using the instruction memory. The second stage is instruction decoder and the register read. So we will decode the instruction and we will read the operands in that stage. The third stage is the execution stage, and the fourth is the memory stage if data accesses are required, and the fifth stage is the write back stage. If any results are written back to the memory or the register, we will use that write back stage. Now see the performance of the pipeline system. Let us assume that the time stages are we are consuming 100 picosecond for register read and write. Whenever we have to read the register or write the register, we are consuming 100 picosecond, and for other stages we are consuming 200 picoseconds. So we would compare the time for the single cycle data path, then we will compare that time for the single cycle pipeline data path. So the load instruction would utilizing, if you see that the load instruction, we have to fetch the instruction, we have to read the operands from the register file, then we have to perform the ALU operation for the physical address computation, then we have to access the data memory, and then we have to write the result back to the register file. So all the functional units are being used for the load word, and the time frame that is being used for the load word is the accumulation of all the time, 200 picosecond plus 100 picosecond plus 200 picosecond plus 200 plus 200, that is 800 picosecond. So it is required that to complete a one load word instruction, we have to have 800 picoseconds time frame provided to the load word instruction. Now coming to the stored word instruction. For the stored word instruction, we fetch the instruction, so 200 picoseconds are added. We read the operands, 100 picoseconds are added. We perform the ALU operation to compute the physical address, so 200 picoseconds are added, and then we write the result to the memory, so another 200 picoseconds are added. But for we don't write anything into the register file, so that time is not being added here. So 700 picoseconds will be required to complete a one stored word instruction. Now coming to the R format instruction. In the R format instruction, we fetch the instruction, we decode the instruction, we execute the instruction, we don't access data memory, and we write the result back to the register file. So any R format instruction would require 600 picosecond in this scenario to in order to complete. For branch equal instruction, we fetch the instruction, then we decode the instruction. The ALU will compare the condition and decides what to upload into the program counter, and that's it. We don't access the memory and we don't access the register file. So in this particular scenario, 500 picoseconds are required to process the process the branch equal instruction. But if we have got the jump instruction here, we only require 200 picosecond to complete. No register file read, no LU operations, no memory operations, no register write. Only 200 picoseconds are required to complete jump instruction. So what would be the clock cycle time which we have to set? If you see this particular scenario, if we set the clock cycle time equal to 600 picosecond, then we can only execute jump instruction, branch equal instruction, and R format instruction. We cannot execute store word or load word in a single clock cycle. So what we have to do is we have to see what is the longest or the slowest instruction that takes the maximum time, and we have to set that time, the clock cycle time according to that. So our clock cycle time for this particular setting is 800 picosecond. Right. Now coming to the pipeline processor, basically the pipeline processor, basically the clock cycle time is dependent upon the slowest instruction slowest stage rather than the slowest instruction in the single cycle processor. So we have to see that what is the slowest stage that is consuming the maximum time, and we have to set the clock cycle time according to that. So this is the basic difference between the non-pipeline system and the pipeline system. In a non-pipeline single cycle processor, the clock cycle time is dependent upon the slowest instruction, that was the load word, and in pipeline system the clock cycle time is dependent upon the slow stage. And in this particular scenario, in the previous example, the slowest stage or the maximum time for any stage was 200 picoseconds. So we have 200 picosecond clock cycle time. But here we've got 800 picosecond clock cycle time. So if you see that we've got the three load instructions simultaneously. So the maximum time to execute three load instructions are 800 picosecond multiplied by 3. So this program with three load instruction will require 2400 picosecond to execute. See, for the first 800 picosecond, first load is being processed or served, but we are unable to execute the second load at the same time, and because if at this particular scenario the register file or the register file and the instruction fetch section was free, but we are unable to process that. At 800 picoseconds, we process that at the other load, and at 1600 picoseconds we process the other load, and that load will be completed at 2400 picoseconds. So that is the total execution time for that load. But for the pipeline system, we can overlap the execution, and the clock cycle time is dependent upon the slowest stage. So 200 with the 200 incremental steps, we have distributed a timeline. So for the first 200 picosecond, we have fetched the load 1 instruction, but when the load 1 instruction is being decoded in the next 200 picosecond, we have fetched the second load at the same time, and when that is executed at the next 200 picosecond, the second load is being decoded and first load is being fetched. So we are not leaving any of the functional units empty or idle. We are fully utilizing our hardware. and in that particular scenario, our execution time is basically equals to 1400 picoseconds. So that program that was in previously been executed in 2400 picoseconds now is being executed in 1400 picoseconds. So what would be the speed up? Basically, speed up is equal to execution time old divided by execution time new, that is 2400 picosecond divided by 1400 picoseconds. And this time will further improve if we've got more number of instructions. So more the number of instructions to process on a pipeline processor, the better the speed up and better the execution time, and better the throughput of the system, right? So I hope so now the difference between the pipeline processor and the non-pipeline processor is a bit clear to you. Well, that was all for today's session. We will be discussing the pipelining later on in later stages. Till now, good day, and we will meet again, inshallah.